And our session now is with Susan Jo Russell from Turk and Deborah Schifter from EDC. So go ahead.
Okay, thanks. I'm Deborah Schifter, and this is Susan Jo Russell over here. This is what we're going to be talking about this afternoon. So to start off, as many people have been saying in the last, particularly this morning, that as the Common Core lays out a map of the mathematics to be taught when, that as with any policy document, its enactment depends on how the words of the standards are interpreted. So we've heard this morning comparing the Common Core to the Constitution, to the Torah, or to church readings. And we don't necessarily need to be that grandiose, but in fact it is a document that needs to be interpreted. And so we're going to be considering a set of standards. So let's just take a look at these. At grade 1, apply properties of operations as strategies to add and subtract. Grade 2, fluently add and subtract within 100 using strategies based on place value, properties of operations, and or the relationship between addition and subtraction. Grade 3, identify arithmetic patterns and explain them using the properties of the operations. And in grades 4 and 5, the standards continue to emphasize understanding calculations, now multi-digit multiplication and division, in terms of properties of the operations. Also, these are just some of the particular items in the standards, but throughout the document, we see a lot of reference to the properties of the operations. Now, some people, and here we might include teachers, administrators, parents, mathematics educators, mathematicians, textbook publishers and textbook authors, assessment developers, that there are likely to be people who will look at these standards and assume that they mean that young children must learn formal terms and associate each term with particular patterns of symbols. In fact, that's the way some of the ideas of the new math of the 1960s were treated, and many of us at this conference were students in those years, and I'm sure that some people will attest to the pointlessness of that treatment of this content. In fact, there is a footnote in the Common Core that says students need not use formal terms for these properties. But our community does not have many images of what these standards can look like as they are enacted in elementary classrooms. And so this afternoon, Susan Jo and I will share with you an interpretation of what these standards could mean and present images from elementary classrooms where teachers and students are working on these ideas. Our talk is divided into 4 parts. First, we'll describe to you our work in early algebra, which we think of as related to a constellation of content and practice standards. In part 2, we present a detailed example of a sequence of lessons from a 3rd grade classroom. In part 3, we'll show some video clips from elementary school classroom where these ideas are put into play, and based on these images, we'll elicit ideas from you about the knowledge required of teachers to enact such lessons. And then in part 4, we'll share some of our concluding remarks. So, part 1, focus on early algebra in the elementary grades. Our ideas, Susan Jo's and mine, are based on work we've been doing with teachers and their students on ideas of early algebra. For the last 10 years, we've had a series of grants from the National Science Foundation to address this content, and we have a 3rd colleague, Virginia Bastable, who's not here today, but the 3 of us have been working on these ideas for quite a while. On this slide, we are identifying our current projects. Our work began probably in the early 90s with the observation that when classrooms open up to students' ideas, students sometimes notice and remark on generalizations about the behavior of the operations and are interested in them. More often, such generalizations are implicit in student work as they learn their math facts or work on multi-digit computation. For example, here's the work of a first grader who was solving a story problem that is solved by 7 plus 6. And she wrote, I know that 7 plus 7 equals 14, so take away 1 from the 7, so it is 13. So Leah, this child, is saying that she knows that 7 plus 7 is 14. Many students do find it easier to remember doubles. And she can derive 7 plus 6 from 7 plus 7. The general idea implicit in Leah's work, the general idea implicit in Leah's work is that in an addition problem, if an addend is decreased by 1, then the sum is also decreased by 1. This general idea can be written out in algebraic symbols, although Leah is not thinking in these terms. So we repeatedly saw these kinds of generalizations in elementary students' work, and so we asked ourselves, how do students understand these generalizations? What happens when teachers structure lessons explicitly to focus on them? And these are the questions that initially guided our study of algebra. So as our work developed, we focused our inquiries on investigating, describing, and justifying general claims about how an operation behaves. This involves a shift in focus from solving individual problems to looking for regularities and patterns across problems. Students represent the actions of the operations with manipulatives, diagrams, and story contexts, and these representations become the basis of proof. And the operations become objects of study in themselves. Students begin to see that each operation has its own set of properties and behaviors, that an operation is more than an instruction to calculate. For another example, when students are learning their single-digit addition combinations, they notice relationships that help them learn that they can solve sums involving 9, like 9 plus 4, by thinking of an equivalent 10 plus sum, like 9 plus 4 equals 10 plus 3. In order to take this idea, which is implicit in the thinking of many students, and raise it to an explicit level for consideration, we now ask, what's happening when you change the expression 9 plus 4 to 10 plus 3? Does this work with other numbers? Does this work with all numbers? How do you know? As students work on these questions, they learn to use a variety of representations to illustrate and justify their ideas. For example, they might represent what's happening with cubes. With this image, they might say, it doesn't matter how many cubes are in one stick or the other. They make the claim, no matter what the addends are, if you subtract some amount from one addend and add it to the other, the total stays the same. Eventually, perhaps in later grades, they represent the idea with algebraic notation. When the students encounter the notation, it is to express an idea they already have in mind. So the notation has meaning. An important issue that we've discovered is that when students work with a generalization about addition, it's important to contrast what happens with other operations. Without that, there's a tendency for students to assume that their claim is about numbers rather than about addition. For that reason, we ask, what happens with subtraction? Is it true that 9 minus 4 equals 10 minus 3? Why doesn't it work? Is there another rule that works with subtraction? Or what happens with multiplication? Is it true that 9 times 4 equals 10 times 3? Why doesn't it work? What does work? As lessons play out, in which students investigate the behavior of the operations, some of the mathematical practices identified in the Common Core become particularly prominent. In identifying and investigating generalizations, Students look for and express regularity in repeated reasoning. As they work to articulate their generalizations, they learn to attend to precision in expressing mathematical ideas. And as they develop representations to explain why these generalizations hold, they construct viable arguments and critique the reasoning of others. In a minute, we'll provide a more detailed example of what can happen in the elementary grades. But let's first take a little time to consider implications for middle school. Here are some examples of persistent errors we see among students of algebra. We might ask, is it the unfamiliarity of the symbols that causes the problem? But another question is, might it be that students who make these errors are hardly noticing the operations or aren't thinking about what the operations do? Here's a specific example. Our colleague, Mr. Lancaster, works with individual middle school students. He wrote to us about one student, Joy, who is struggling in algebra. Joy's teacher uses diagrams like these in class. When Mr. Lancaster presented Joy with a diagram on the left, she easily filled it in, as shown on the right. But then Mr. Lancaster asked her to write the equation that it represents. She could write one expression, the sum of the terms she filled in, x squared plus 4x plus 2x plus 8. But she's not sure how to represent the expression in factored form. She tried x times x plus 2 times 4, but this didn't look right to her. So she tried 4x times 2x. If Mr. Lancaster had simply presented her with 4 plus x, x plus 4 times x plus 2, she might have rules to solve it. She does know rules for filling in these diagrams. But he's trying to find out why she's having trouble. As she's manipulating this notation, she's not visualizing the multiplication and addition relationships and how they interact. She doesn't see how her diagram already shows two ways to represent the area of the large rectangle. This is not simply a matter of difficulty with notation, but about the behavior and representations of multiplication. When Mr. Lancaster wrote to us about Joy, he also explained why he believes a focus on the operations is important for his students. I'm going to read to you what he said. It's a fairly long quote, but I think it's worth it. So bear with me. He wrote, "I've been wondering for a while what the fundamental difficulties are that students encounter in mathematics at the middle school level. I used to think the fundamental difficulty had to do with the introduction of variables and with expressions and formulas. More recently, I've come to think that an even more fundamental difficulty has to do with the understanding of multiplication as distinct from addition. I'm not talking about whether students know their multiplication facts, and I'm not talking about whether students can memorize different sets of rules for things additive as for things multiplicative. The conclusion I'm coming to is that the students who have the deepest trouble with middle school mathematics are those without a clear and rich set of models for what multiplication is and how it's different from addition. In the absence of such models, the students tend to rely increasingly on memorizing rules and how-tos, and their grasp is tentative and fragile. They have given up trying to make sense of what they're doing and instead rely on their well-honed skills of guessing what the teacher wants. To my surprise, this includes many of the students who have decent grades and who can get by quite well with symbolic manipulation of formulas that may hold very little meaning for them." Now, this is an eloquent statement from a teacher about issues in the teaching and learning of secondary mathematics. Implicit in his statement is that students need to develop images of the actions of the operations and representations that embody those images. It's critical for understanding basic principles that underlie both arithmetic and algebra. So now Susan Joe is going to give an extended example from a third grade classroom.
Okay, so keeping in mind some of those middle school issues, as I go through this example, you might think about, so what can now happen at the elementary grades? What can this work on properties of operations looks like that sets up middle school students for making connections between arithmetic and algebra in a more meaningful way? And I should just mention that except in the videos, These are all pseudonyms for both teachers and students, but real things that happened. So a look at a third grade class. So ultimately, what we're considering in this conference is knowledge for teaching. So you might want to attend specifically to what's happening in this sequence of lessons overall. What is the teacher doing, and how does she help her students articulate and represent and make arguments about their claim? So we'll come back to these questions later. We do want some audience participation, even though it's after lunch. But we'll do that with the videos. So how is multiplication different from addition? So as the teacher, Alice Kay, planned this sequence, this instructional sequence, she especially wanted to highlight for her students, third graders, how addition and multiplication behave differently. So her plan was first to investigate with them what happens when 1 is added to an addend, and then consider what happens when 1 is added to a factor. So she starts out by posing this set of problems and asks her students what they notice. After they've worked for a while individually and in pairs, the students come together to articulate a claim about what they're seeing across these problems. So they first suggest, in addition, if you increase one of the addends by 1, then the sum will also increase by 1. But some students think more needs to be specified, and they revise their claim. In addition, if you increase one of the addends by 1 and keep the other addends the same, then the sum will also increase by 1. And just as you're looking, this isn't one articulation that just comes out perfectly from a student immediately. This gets worked on in the group. So Ms. Kay now asks the class, how would you go about convincing somebody that this statement is true? What would you do to convince yourself or someone else? When some of the students, in fact, say that they aren't convinced themselves, she revises the challenge to the second question. So students go off and work on this, and they have different ideas, as you would expect for 8-year-olds, about what an argument would be. And so here's some of the things that get produced. So one group of students presents this as their argument. So if it works for numbers of this size, it must always work. And we see this pretty commonly. So these third graders are certainly working through what it might mean to make an argument for an infinite class of numbers. But let's look at one of the other ones that really is more of an argument. So at first glance, this is Megan's poster, part of it. You'll see the rest in a second. So at the beginning, it looks like Megan's made a similar kind of argument with smaller numbers. She just has an example here. I've got 3 things in one hand and 3 things in the other hand. If I add one thing to one of the hands, my sum increases by 1. But she's actually using her picture. She's thinking of her picture in a different way, as an image to make a claim for any numbers. This is what she says about her representation. And this is why when students are making arguments, you need to look at what they've produced and what they're saying about what they've produced together. This is what she said. The picture could be used for any numbers, not just 3 and 4. I could have started with anything in one hand and then anything else in the other hand and put them together. If I got one more thing in either hand, the total would always only go up by 1. So she can imagine, she says, that this can portray any quantity. Now she's probably thinking about positive whole numbers, not really any quantity. And that the result of adding 1 would always be the same. So after working for a while on adding 1 to an addend, the class goes on to consider adding 1 to a factor. And Ms. Kay poses a similar set of problems about multiplication and gives this writing prompt. In a multiplication problem, if you add 1 to a factor, I think this will happen to the product. So we're actually going to pause for a minute here, and we'd actually like you to just write out for yourself how this claim might be articulated in English, just in words. How would you finish the prompt? You can talk to somebody or just jot it yourself. Okay, so we're not going to give you a lot of time for this. But keep in mind how you thought about it. So the class goes on, and this is what Ms. K wants them to investigate. So here's the task. She asked them to choose one of those original equation pairs, and then either draw a picture for the original equation, then change it just enough, these are her words, to match the new equations. Or make an array for the original equation, then change it just enough to match the new equation. Write a story for the original equation, then change it just enough to match the new equations. And what we want to highlight for you is one of the students' ideas that Ms. K chose to bring back for everybody to consider together. And this is Franny's story context. There are 7 jewelry boxes, and each box has 5 pieces of jewelry. There are 35 pieces of jewelry altogether. And then, as the students are considering this, Ms. K asks, is this story about multiplication? How do you know? Lila says, because there's some amount of boxes and some amount of things in the boxes, and how many things are in that many boxes? Teacher, does that sound like multiplication to you? Students say yes. The teacher asks, anything anybody wants to add to make absolutely sure it sounds like multiplication? Grace, instead of boxes, it could be groups. So there are 7 groups of 5 pieces. Is it important that each box has 5 pieces? What if some boxes had 3, and some boxes had 4, and some boxes had 1? Jonah says it wouldn't be multiplication. How can you change the story to make it about 8 times 5? So Ashley, we'd like you to think about that for a second. So here's Franny's context, 7 boxes with 5 pieces of jewelry in each box. So how's the picture going to change if we change the expression to 8 times 5 in this context? Okay, so we have another box. And so the students in Ms. K's class say that when the first factors increase to 8 boxes, the product increases by the number in one box. And then if we go back to the 7 times 5 picture, now what's going to change in this context if the second factor is increased by 1? So it's 7 times 6. Right, so now when the second factor is increased, the students say the product increases by the number of boxes because there's 1 new piece of jewelry in each box. As the discussion continues, the students explain that it doesn't matter how many boxes you start with or how many jewels are in each box. If you add 1 to the first factor, then you add a box, and the product increases by the number of jewels in a box. But if you add 1 to the second factor, you add 1 jewel to each box, and the product increases by the number of boxes. So now Ms. K is asking them to articulate what their claim is at this point, having done this much investigation. And here's a couple of the articulations of the claim. The number that is not increased is the number that the answer goes up by. The number that is staying and not going up increases by however many it is. So this articulation becomes a really important piece of work here. I think that the factor you increase, it goes up by the other factor. So these are some of the ways that individual students started to work to articulate the claim. Now also, some students suggest thinking of the multiplication expression as A times B, because this idea has come up before in the class, that you can use letters to represent the idea of any number. So Addison says, if you increase the first number by 1, you increase the answer by the second number. Like if you increase A by 1, you increase the product by B. If you increase B by 1, you increase the answer by A. So Ms. K now, though, wants to help students who are taking this in maintain the connection between the symbols and the context. This is important for the learning of these students. Ms. K recognizes that as students are just at the beginning of learning about multiplication, they will be served by staying close to the representations and contexts in which multiplication is used. She's not aiming for all students to learn and use symbolic notation at grade 3, but she accommodates the students who are interested in the idea of a letter standing for any number as part of the class's investigation. With the context of the jewelry boxes well established, students will be able to continue to ground their reasoning in this context as they work on understanding how multiplication relationships work and how they differ from additive relationships. And Ms. K says back to her class, I love this context because you can have any number of jewelry boxes, each one with a certain number of jewels in it, and the product is going to be that multiplication. And if you increase the number of boxes, you get an increase by the number in each box. If you increase by 1 jewel, the increase is the number of boxes because each box gets 1 jewel. And the students came up with other stories as well. This sequence continues for quite a while. This isn't something that she just does in one day from beginning to end and it's over, but they come back to these ideas. They also use a variety of diagrams and discuss how the story contexts map onto their diagrams. And they do the same with arrays. And according to Ms. K, the energy of the class remained very high throughout this discussion. And this is of interest to us, that these ideas about how the operations work really engage students at a fairly young age. So before we show you a few video clips, we just want to make some observations. The properties of the operations and special cases of them, which many of these ideas are worthwhile objects of inquiry. We could think of the investigations of Ms. K's class as inquiry into a special case of the associative property and a special case of the distributive property. From the work this class did to interpret what was happening with addition and multiplication, we can infer that if properties were simply presented to students, they're unlikely to be understood and readily accessible for application. But rather, the properties are objects of inquiry themselves for these young students. Even the special case of the associative property of addition, adding 1 to an addend, was engaging to this 3rd grade class. But it's the contrast with multiplication that we think makes it especially powerful for 3rd graders. I've lost my cursor. There are other generalizations about the behavior of the operations that are worthy of attention. They may not have names, but they hold equal weight in the world of the elementary school classroom. For example, this generalization that if you add an amount to one addend and subtract that same amount from the other, the sum stays the same, is one that many students notice and apply in their computation work. If you've worked with one students, they often come up with this. This is also a generalization that they can explore with representations. They're not going to think of it as an application of the associative, commutative, inverse, and identity laws, but especially there are generalizations to be explored about the nature of addition, subtraction, multiplication, and division. It's important that students see each of these operations as having its own set of behaviors or generalizations to investigate. And then keeping symbols connected to representations is key. Key to elementary students being able to reason about the behavior of the operations. Eventually, we want students to learn to function in the abstract, but we want them to retain the capacity to show how ideas can be represented and to move back and forth between these worlds. As illustrated earlier, this is missing for many algebra students. We don't think about diagrams and manipulatives and pictures as crutches for the students who don't get it, but as essential tools for thinking, and especially at these age levels for constructing mathematical arguments. For example, in the jewelry box example, students could use that image to make a general argument about how their claim about adding 1 to a factor holds for positive whole numbers. So we want you to keep this example in mind. And as we move into looking at some video clips, we'd like you to think about what it would take for teachers to be able to incorporate this kind of work on this constellation of both content and practices into their classrooms. Some components of investigating a generalization are helping students notice regularity, articulate general claims, investigate through representations, construct arguments, and compare operations. And we're going to show you a clip for each of these. And as you look at each clip, we're going to give you just a little bit of time after each clip, just a couple of minutes, to talk to somebody next to you about the following questions. What is the work of the elementary teacher? And what mathematical knowledge is required in each of these 5 areas? And we're really asking you to help us think, kind of in light of Deborah Ball's remarks the first night, about that we need to be identifying practices in more specific ways. And so we're really asking you to help us think about this. So our first clip is about noticing regularity. And all of these clips, we're not presenting these particularly as perfect exemplars. These are just little clips out of classrooms, out of long sequences of work. And we really want you to just use these to be thinking about what's the work of the teacher here. Not what should this teacher have done better, but what is it that teachers need to understand? What is it that teachers need to know to do this kind of work? So this first clip shows a class of first and second graders thinking about the relationship between addition and subtraction. And they've been looking at these problems. Maeve had 7 red flowers. She also had 19 yellow flowers. How many flowers did she have altogether? Peter caught 19 fish in the morning. He caught 7 more in the afternoon. How many fish did he catch? And Elizabeth had 26 balloons. 19 flew away. How many did she have left? Can you use what you know from the previous problems to help you with this problem? How does it help? So we're joining this class at the point where they're beginning to consider this third problem.
The second, oh, yeah.
Isn't it the third problem?
Well, they've talked about the addition and they
Yeah.
haven't talked about the subtraction yet.
The subtraction, right. And the teacher has asked these questions. Can you use what you know from the previous problems to help you with this problem? And so now they turn to the subtraction problem about the balloons flying away. And this is just about 2.5 minutes. So as you're watching it, think about, in terms of helping students to notice regularity, what's the work of the elementary teacher and what mathematical knowledge is required. Okay, oh, this is, I have to go to my DVD player for this one. This will just take a minute.
I actually want to move on to the next problem, because the next problem said that Elizabeth had 26 balloons, and 19 of them flew away. So first of all, how could we use these to show the story about Elizabeth? Anybody know? May? How can we use these to show the story about Elizabeth?
Well, first of all, you have to get more cubes to show it.
I can't use the ones I have here, the 19 and the 7?
No, because you don't have enough.
I don't have enough?
Yes, you do. Yeah.
Jesse, say it louder. What did you just say?
I said yes, she does.
You think I do have enough?
Yeah, because that's all you had throughout the whole thing. 19 and 7. Yeah, and then it just still need 26.
What'd you say, Kelly?
Still need 26.
I still need 26. Do I have 26 here?
Yeah.
How do you know I have 26?
Because 9 plus 19 is 26.
I have 26.
You just have to add them up differently.
How about if I...
Like all together.
All together. Okay. So I need them all together? Okay. So what are these? So now in this problem, we're going to call these Elizabeth's balloons. Okay.
Yeah, and they fly away. Okay.
And what do we know in that problem? 19 flew away. 19 flew away. So
Fly away.
you want to make them fly away? Or you want to make them fly away? May, how did you know to break it right there without counting anything?
We knew these were the 19.
Because you know those are the 19. Don't worry about it, sweetheart. Okay?
And then you would only have these left. Because these flew away.
Okay. So have a seat, Maeve.
And
Christian, what did you want to say? Oh, we're not going to actually make them fly. So here's the question. Peter and Jesse had been working really hard to figure out how to answer the question, how did solving the problem about the fish and the flowers,
the fish and flowers were easy.
how did that help you to solve the problem about Elizabeth's balloons? Well, first of all, did it help you in any way?
No. Yes.
Okay, so going back here. Oop, always miss that. Okay, so just for 2 minutes, just talk to somebody near you about what is the work of the elementary teacher in supporting students to notice regularities, you know, kind of using this clip as fodder for your discussion.
So they like the clips.
Yeah, really. That was good. I think I'm going to warn them, so Nikki's is the next one. I think I'm going to warn them that it's slower paced and they need to try to pay attention.
Yeah.
Are you timing by any chance?
Well,
or- I don't
yeah,
know.
so-
I can, actually, there's a second hand up there. I can
Yeah.
look. That really is a cute clip with all the other things she's covering because it's so first grade. Yeah. I wonder if we should have had them jot down anything.
That's what I had been thinking.
Yeah.
So maybe now, for the next one, you
For
can
the
say,
next
you
one.
might want to jot down
Yeah.
some notes.
Well, I could say, jot down one sentence about what you were just thinking.
Yeah, we'll just do that.
Before I
Yeah.
just
yeah.
ask everybody to do that individually.
Yeah.
Okay.
So are we saying 2 minutes?
Yeah.
I think it's,
Okay. Well, that's at least, that's 1 plus something. I didn't
Oh,
start
okay.
looking at the second hand at the beginning. I'll give them another 30 seconds.
all right, no, I'm going to stop. So, and maybe we don't, it might be that we don't need the whole group, the whole group to be as long.
Yes,
So,
right.
yeah.
Yeah. Okay, I'm going to ask you to bring your discussion to a close. Okay, we're going to ask you, we're not going to have a discussion right now until we've looked at all the clips. So we'd just like to ask you, everybody, to jot down a sentence or a phrase about what you just talked about, just to hold on to it before we do the next clip. Yes. That was first and second grade. I don't know. Okay? So now we're going to think about articulating a general claim. So this third grade class that you're about to see has been investigating subtraction. And they first did a sequence on the kinds of pairs of problems on the left, where the first number in the expression stayed the same and the second number changed. So they had worked on that previously. Now they're working on the kinds of problems on the right, subtracting the same amount, but the first number is different. And so the teacher at this point, it's fairly early in this investigation. She's brought students together to discuss how they might formulate a rule for such pairs of expressions. And you're going to see about 5 minutes of this. So I want to warn you, this is a slower pace than was just going on with the first graders. There's lots of pauses. And so just be aware of that as you're trying to concentrate for 5 minutes. Also because the teacher is recording, and so that takes a certain amount of time. So, and again, where's my questions? Here's my questions. Be thinking about what's the work of the teacher in supporting students to articulate a general claim and what math knowledge is required.
Can I ask you a question? Those pairs, are they, the situation is not symmetric. So are they thinking about the first one and then how is the second one related to the first? Or
Yes.
the other way around?
They're thinking about, well, she's been giving them the pairs together. And yes, generally they think about the first one, so 10 minus 3. And then what's the difference? And then how does the difference change for 9 minus 3? Yeah. Okay. Here we go.
And I want to know, right now, what is the rule that we have come up with so far for our subtraction sequence, our subtraction lessons? And all those posters that we've done, they're all up on the front of the board. What's the rule that we've come up with so far? We've all written something, so we should see more hands. All right. Keep thinking even though someone's talking. See if your ideas are a little bit different. Rashad?
If you take away the short answer, you would get a bigger answer.
If you take away a short answer, you get a big answer. Okay. Sarah?
If you start with a big number and take away a small number, your answer will be bigger.
So if you start with a big number and take away a small number,
Your answer will be big.
your answer will be big.
Keep on going.
Are you not finished? Okay, keep going.
And if you take away a small number, if you start with a small number, and take away the same amount, you will get a small answer.
Did you say small or smaller? What did you say?
Small.
Small.
Smaller.
Smaller. Okay, good. Sorry, I thought you were done up there. Good. Also want to share? Okay. Let's have Linnea share.
Sometimes when you're taking away, sometimes you get a big number. And
Mm-hmm.
And like 40 minus 10 equals 30, and 50 minus 10 equals 40. So when I took away half, like I took away 10 from the 50, I got 40. So when I took 10 away from the 40, I got 30.
So you said when you are taking away, sometimes you get a bigger number. So you just pointed out in your examples that you're taking away 10 both times. And your rule that you just said, when you're taking away, sometimes you get a bigger number. Which one of these gave you a bigger number?
The 50.
The 50 take away 10 equals 40. So if we went back to the very beginning when my question was who has more, her example here, this person, whoever had 50 and took away 10, now has 40. That person ended up with more. Why is that? You need tissue? Why did this person end up with more? If they were stickers, they were apples, they were whatever. Adima?
Because 40 is 10 more than 30.
So the answer 40 is 10 more than the answer over here, 30. Okay, so this is 10 more than 30. Sarah?
Because she started with the bigger number.
So this one started with the bigger number. Tyshawn?
And she started with 50, and the other person started with 40, and 40 is 10 less than 50. That's why it's going to be 10. That's why the person that started with 40 and ended up with 30 is going to have 10 less than 40.
Okay. So we'll just give you a couple of minutes to talk about these questions. I wonder how people are going to take that. It'll be interesting. So, what do you think why was Hai asking that question?
I was wondering if he didn't understand that you said she first
Did
the
those,
ones on the left,
and then that's what I was wondering too.
I think that's what he meant,
Okay.
and so he
Right,
was thinking that the two columns they're not equivalent, they're not the
right,
same, they're
right.
getting at different ideas. I
Right.
think that's what it is.
Okay.
All right, that's what
But
I
he seemed to get it when I said it, so
Yeah.
okay. I hope my mic isn't on when I'm saying things. Who is Steve?
No.
Oh, here. Oh, the sound guy. The sound guy. Yeah. Oh, so you're doing the next one,
Yeah.
and the next one is
Fran.
Okay. I wonder if they're going to be focused on the kids and what were the kids saying, and
But
were they
even if
not
they-
right, or were
Even to be thinking, I mean, if they start talking about that, then they're still. So
what does the teacher need to be able to do? I mean, I think, yeah.
they've been given enough time.
Oh, I think so. Have them write something down.
Okay. Okay, we're about to go on to the next clip. And so if you want to just take a moment to jot down an idea. So in the next clip, we're going to be looking at an example of investigating specific cases of a generalization through representations. This is a group of fourth graders. And they've been noticing that in a multiplication expression, if you double one factor and halve the other, the product stays the same. So in the lesson that, from which these clips are taken, students are creating representations for this specific case. 10 times 3 equals 5 times 6. So.
And it's in two parts.
It's in two parts. Oop, what happened? I want to go here.
That's what I was doing before.
If I go, no.
Fourth.
This is fourth grade.
Is it not, you're not getting a little, there it goes. Okay.
Oh. So what's supposed to happen?
Is it not going?
No.
You have a little hand. It's not going? All right, let me just fiddle for 1 second. Sorry. Okay, I forget how I got out of this before. What is this number? 62. Okay, 61. 61 you want to be on. Yeah. It's not doing it. Well, I can run it from the, from this. I don't know what else to do. All right, sorry, I have to run it this way. I don't know why. Oh no, this isn't showing either. Rats. Oh, why did you click that? No, this is what happened before. Okay. Yeah. I'm just going to load it. So you're trying it again. Yeah. 62.
61 is what we want.
Okay, please work. No. Okay, I can run it just from the clip.
Yeah.
Okay. Thanks, Paul. Oh, I don't know how to run it from here.
Just follow Paul's instructions.
Yes, I will. Okay. Oh, go away. Oh, it's just loading? Is it just loading? Oh, where is it?
Oh, it's way
It's
up
over.
here.
Oh. Go, ah!
On top of the other part.
Okay.
and then the array looked like 5.
Could you explain to me what you did?
I did 10 times 3, and then I broke it in half, and then I took the half and put it on top of the other part. And then the array looked like 5 times 6.
And what is that proving?
That 10 times 3 is the same as 5 times 6.
Okay, so we want, all right,
We'll get the other one.
well, actually, no, we first want to look at the last.
I don't know that I can get that to happen.
Let's give it a try.
Could you explain to me what you did?
Okay, what we want to do is actually see
Same as
if we can just, if you can make out what she actually has written. So at the bottom she said, first I made an array of 10 times 3, and then I split it into equal sides, and then took one part and put it on the other part, and then the array looked like 5 times 6. So that's what she had written. And at the very end, Susan Joe was behind the camera, and she had asked her to explain it, and didn't have enough time to before the teacher called the class together. But that's what she had already written down.
And then?
And so then the class came together, and Lily put her diagram up on the poster, but the teacher had this boy explain it.
And then I shaded it that area.
Okay. Is it okay, Lily, if we do what he did on yours? Where are you, Lil? Okay, you want to do it?
Whatever. And then
So you took so who can say what he shaded and how much of the 10 by 3 array did he shade in? How much of the 10 by 3 array did he shade in?
you shaded in half of it.
Half of it. So you took half of the 10 by 3 array, and Lily did too. And then what did you do?
And then I added it on top. And
So what happens when you add it on top?
it's technically doubling the 10 because this is the 10 part.
Doubling
The
the,
10 and then making this 6.
so you half the 10.
Yeah.
And you took that and put it up there.
Yeah.
And then that made the
Yeah. And they
The
both
3,
equal.
so the 3 doubled.
They both have 30 squares.
So so the 3 doubled, he doubled the 3 and half the 10. How many people did that?
The task was to come up with a representation to demonstrate why it works, that 10 times 3 equals 5 times 6. Yes,
But they knew that they are equal to begin with.
that's right.
And that's a lot different than, suppose you did this with another product. Suppose you had not started out with 10 times 3, but you started out with 12 times 8.
Right.
And then you applied the same process. It seems to me that would have gotten it a little deeper. But I can take half of one because I doubled the other, because I don't know what the answer to that second product is going to be.
Okay, so we're going to have a whole group discussion about some of these issues, and that might also, what you're specifying, might also lead into what is the work of teachers here. And so again, I want you, so there are 2 more clips we want to look at before we sort of open it up, and you'll be able to refer to each of these specifics. But for now, if you just look at this one, what is the work of the teacher as they are focused on looking at representations of specific cases of the claim that they're working on?
You're talking now.
Yeah. No, yeah. You get to talk now to your, or take some notes and.
Yes. Okay, so then we have,
Let's check. Oh, so we're back to.
I'm back here, but I don't know if it's going to work. So let me
Okay.
just see. So this is the. See, it's not giving me the little hand. I don't understand why.
So we'll go back to.
So we'll go back to the other way of doing it. So maybe I'll just. So you know what? Let me get set up for the DVD. This is extremely annoying. We have like 3 different. Okay, so this should be set.
Okay.
And we can put it in full screen. And I think I'm just going to, let me just get the other one set up. So. Oh, I see. It's putting it on funny. Oh, it's copying it here. Oh, good. Maybe I can get both of them.
Okay.
I have a challenge for you.
All right. Let me get the other one there. Okay. Yeah.
Oh, that's the sound. It's this goes back to.
There. Okay. And see if this works.
All right, so just with your eyes right now, just look around.
Okay, did I lose the first one now? Yes, I did.
I have a challenge for you.
About to move to the other clip, and so if you want to take this time now just to jot down some notes. And we had actually thought that we got this technology all set up.
No, wrong one.
Back. There. Or this.
Okay.
Okay, so in the next clip, we're going to look at third graders constructing arguments and using representations. And this is a class, again, a different class who worked on this, claim. In addition, when one of the atoms goes up by 1, the sum always has to go up by 1. So the class had done the work to get that articulation that they're all agreed on, and so now the teacher is giving the class the challenge to prove their claim. So we'll first see the way the teacher presents the challenge, and then we'll see the beginning of a discussion after the students have worked in pairs on that challenge. So, no, you want to go to
I have a challenge for you. You all seem so convinced about this, and I really want to look at this same kind of idea with some other operations, because Nat was raising this question the other day. I wonder if this kind of thing would work with other operations, which seems to be a really interesting question. But before we do that, I want to get us really able to convince somebody else that this would always be true, because not everybody has had the chance to go through the days of work that we've already had. For instance, Group M hasn't been looking at some of these ideas yet. Mr. Lightman, Ms. Reed, Ms. Ramsey, right? Ms. Ananda. People haven't, outside of our group, haven't really been looking at this idea yet. So I thought, well, let's take today to see if we could find a way to convince somebody who wasn't here that this would always have to be true. And to do that, I wanted you to think about, could you use, so we've used examples to convince ourselves that we haven't yet found one that doesn't work, but could you use a story, context?
But
Remember Aya had that great, the number of word pages, story, context for looking at equivalence in addition? Remember the book pages, here's a book that's this long, or we had the flower beds on two sides of the road, and this number of flowers here, and this number of flowers there. And so can we come up with a story context for this rule that would convince somebody, oh yeah, obviously, that always has to be true. That's got to be something that's always true in addition. Or could you come up with some kind of a model or a picture with snap cubes or some kind of a picture where you could show that's always going to be true? Or could you use a number line to show that that would always be true? Vera?
well, since numbers go on forever, how do we know that like I was like trying to convince somebody out of our group, like I wouldn't necessarily do one of those because I wouldn't be able to assure them that like with a number like extremely high that it wouldn't work, because like we probably don't have like so many snap cubes that like we could like do any number on the world and it would still work.
So you get what Vera's asking about?
Like how?
So Vera, I think kids are getting what you mean. I have a question to ask you. You've actually raised the challenge a little bit.
I would ask like if they knew a little bit, I would like that we were doing this.
Can you hold that thought for one moment? I'm going to give you a question to move this. I think this is going to address some of what you're asking about. So how could you make your story or model or picture or number line? If you are like Vera, and Nat, you're Vera's partner, right? So when you and Vera are working together today, this might be the challenge you want to take on. How could you make your story or your model or your picture or your number line general enough that it would assure that somebody would say, oh yeah, that really makes sense to me. I couldn't ever find an exception to that. That would always have to be true.
Okay, so the discussion goes on a little bit more, and then the students set off to work in pairs to actually do this task, and then the teacher brings the class together, and we're going to see just the beginning of that discussion.
Right. All right, so just with your eyes right now, just look around the room and see what you notice about what's similar mathematically, about what's on people's boards here. What do you notice is similar? Yeah, if everybody can put their stories down so that people can see the models. Does anybody have a comment before we hear more particulars about people's ideas? What do you notice about the models? Maddie?
Well, in all the models, there's like one more added on to it. Like in ours, there's like one more added on to it. And theirs, it's like 5 and 4.
Uh-huh.
And then this one, there's one more.
Do people see that? Looks as if there's one more added on. I don't know if people can see Nat and Vera's over here. Does that follow also? Yeah?
I think so.
So does that seem important?
Yes.
for a rule?
Yeah.
Yeah, that seems promising, right? So, Eli and Lucas, can you tell us about yours?
Well, it says brown plus brown equals who cares? It doesn't, we thought it didn't really matter what the sum was that time. But then we added a red. So the brown plus the red equals who cares plus 1.
Patricia, who cares, huh? So, and by who cares you mean?
Doesn't matter.
Doesn't matter. Yeah.
I just sort of like that.
Yours is sort of like that?
Yeah.
Can you say why, Oscar?
It's like, it's green plus yellow equals any number, basically.
And green is how much?
Green doesn't, well, green.
It doesn't matter?
Doesn't matter. All green is more than this.
Oh, green is more than the other one, and that matters? It has to be more?
No, doesn't have to.
Oh, it doesn't? Okay.
Yeah, but this is just what.
Uh-huh.
And then it's green plus yellow, which is more. And this yellow is more than that yellow, which does matter. So that the sum would be 1 more.
So,
Because it's like, so this number plus this number equals a sum. And then this number plus, then this number, this same number here,
yeah?
plus this same number plus 1 equals this sum plus 1.
Okay, so once again, we are asking you to think about what is the work of the teacher in supporting students to construct arguments, and what's the mathematical knowledge that's required here. And we'll give you a few minutes to talk about that before we show one more clip.
Maybe 1 minute. Let's see, does this one need setup? Oh, yeah, it does. Yeah. Switching the add-ins. Maybe I can just say it. I'm trying to. So we have 15 minutes left. Yeah. So I could just say this, and so I can go right to the DVD. You know, it's funny that. When I moved the cursor over a little bit, I got the little hand, like it wasn't in the right place or something. It was weird. And then it worked. That was just accidental. So. Okay. You want me to introduce this one? Or?
Yeah, you can do this whole thing, and then we can just move into
The discussion.
You
Yeah.
can both stand up here.
Yeah. And I'll try to, maybe we'll say something about, try to keep the, you know, you probably have, there's lots of questions one could ask about what the students understand, but we're really focusing here on, you know, on what is it teachers need to be able to do and to understand.
What is the work of the teacher?
Yeah.
And I think that sort of Zal's raising something that is an issue that actually it's not so straightforward.
Yeah. What he, you know, I was
saying that it would have been better if the kids had been working with numbers where they didn't know that it was so
the
clear.
same. Yeah. Right.
But
that is a judgment, though. I mean, that does connect to what the teachers have to think about. Yeah.
And that sometimes it's important sometimes it's more useful to work with familiar numbers.
Yeah.
And sometimes it's more useful
To work with,
numbers
right,
where it's
right.
still not exactly.
Yeah. So people do seem to be really talking. That's good, pretty much. And we do want to, so I think we'll just do our last slide. I don't think we need to do all the other stuff at the end of the, I mean, we'll do the discussion and then just.
Oh, and not have our own take on it all?
No, that we should do our slides on our take, our 2 slides on the what teachers need to know.
Oh, without having discussion from
No,
them?
have the discussion, and then do those slides,
And then
but
that's
not
it?
do the pillars of computation and so
yeah.
it just doesn't seem like
Yeah,
we need
that's
it.
not good. Okay,
We only have 15 minutes.
okay, yeah. So,
Okay, so are
do
we
we want
ready?
to do the last one about the kids in that last
Oh.
multiplication example?
Yeah, we could. Yeah, yeah, sure. Yeah. Okay. We're going to stop you once again. And so as you're stopping talking, if there's something you want to jot to remember for our discussion in just a minute, please do that. So this last clip is a second grade. And they've been working on the idea of commutativity in addition. And towards the end, and we're not going to see that they've done quite a long discussion about that and have modeled it and talked about it, looked at it with small numbers, looked at it with large numbers. And so this is the issue about contrasting operations. So towards the end of this, the teacher is thinking about, well, so did they think that this rule that they've come to is just about addition? Or do they think that this works no matter what the operation is? And so she poses the question about subtraction, and we're just going to see a little bit it's the very end of a long class.
So your day help you in any way?
Well,
You want to tell us how?
oh dear. Okay, sorry.
And is this one all right?
I hope so. I hope so. If not, I did something wrong.
If not, we'll just read about it.
Oh, I could just get to it quickly.
You don't have to go through the whole.
I think somehow they're both set on. Because I took one out and put one.
I know the last problem that
Okay.
See if I could do this really quickly. Just skip it.
Okay.
Okay.
We've just decided
Sorry.
to skip this
Too
one.
many technical difficulties.
But
yeah.
essentially, the children are going through an explanation of how they know that 4 minus 7 is not the same as 7 minus 4.
And
they come up with.
Yeah, and I can actually say that, so remember these are second graders. So several students say things like, well, you can't subtract 7 from 4 because 4 doesn't have 7, right? And if another student says, and so it would just be 3, 2, 1, 0, 0, 0, 0. And then finally, at the very end, a child who's been waving his hand says, well, it wouldn't be 0, it would be -3. So he's bringing in an idea that he's, heard, experienced somewhere. And he kind of explains that. But all of them, even those who are the students who are saying, you can't do it or it's 0, are getting the idea that subtraction is working differently than addition, which is what the teacher had intended to get at. So that was the last clip.
So at this point now, we would like to open the whole group discussion to the ideas that you've been discussing. We do have a list of the clips that you just listened to help us talk about them. But we'd just like to spend a few minutes to hear sort of what in this work, what is the work of the teachers in engaging their class with this set of ideas? And what is it that the teachers need to know?
And we know there's a lot that one could say about the students. We could analyze this in a whole different way, but we really are focusing on what teachers need to understand and do. The person with the microphones has control.
power.
That's okay. Bill has one.
So I think it was the last clip that we actually saw. My question is, the teacher appeared to have deeper content knowledge, and almost like she was backwards mapping mathematically where kids would be going in the future and enabling them to have prerequisite skills at their grade level for eventually getting there at some time in the future. So what enabled that particular teacher? What was her math background? How much work did she work? How much time did she spend with the two of you even concentrating, focusing on those kinds of issues so she knew how to bring up the important mathematics at their level?
And what is the evidence that you, I mean, so you started out with the assumption that she had knowledge that the other teachers didn't have. And so can you say more specifically what it is that you noticed that she was doing that depended on that knowledge?
Randy and I were having a long conversation about this.
So what's really interesting in a lot of these clips, I'll pick one. It doesn't matter. Clearly for the teachers, these tasks were not about getting an answer to a specific problem. They were about seeing relationships. And that's kind of extraordinary for watching teachers who recognize in all of them. So it was, I think, the one what is the 10 minus 4, 9 minus 4, 27 minus 14, 26 minus 14, the 10 times 3, 5 times 6. All of these cases weren't about 10 times 3 and 5 minus 6 for the teacher. And the way that she was orienting the students, the questions she was posing, the way she was asking them to go back and try to come up with things, the reaction to Vera's comment, which was really about, I'm not exactly sure what Vera was, where she was coming from. I sort of assumed she knew that they didn't have infinite blocks, and she was pointing it out, and the teacher kind of recognized that the students were aware of that. But then she leveraged that to say, okay, so so how could you make your story or model or picture or number line general enough so that it was assured that somebody would say, oh, that has to be true. Everyone would see that. Again, all the teachers recognized what this game was about. And I'll make one more comment about what's in people's minds that I thought was interesting. Earlier in the presentation, Susan Joe said they're about to look at the third problem, and Deborah said, no, the second problem. And then, because Deborah said they looked at addition, and you considered the first two additions as one class of problem, the addition, and now they're looking at subtraction, and Susan Joe is counting the individual problems. And again, it's another example of how what's in your mind is sort of guiding the big picture. You were looking at the classes, which is sort of what the teachers were doing, too.
So I have a few things to say. So you're both making important points about teacher knowledge, and you're also asking some questions. So I'm going to sort of make some points in response. One, that you're saying that they are engaging in a whole process that's really different from what you see in most classrooms. And all of the teachers that you see on these clips have been working with us on our projects. So we haven't just gone into classrooms randomly. These are teachers who have worked with us on these ideas and are making very serious attempts to put them into play. Some of what the teachers told us, so we were working with the teachers on this idea about generalizations for some years. Some of them have been working with us longer than others. The least of them at this point had been working about 2 years, at least 2 years. So when we started working on generalizations, they regularly had an assignment to focus in on a generalization and write up a narrative about what happened in their class. a couple of years into this process, the teachers started saying to us, you know, we used to think that the number and operations strand was about understanding numbers and about computation. And now we're seeing that there's this third component that is as important, and it's about exploring the behavior of the operations. And that they used to think that every time we gave them this assignment to write an episode about a generalization, that they would have to come up with some special activity to do that. And now they realize that this idea underlies all of the work that they do in number and operations, or at least all the work that they do in computation. And so that's one thing, and it feels that there's an important message that in order to do this work, that's an important realization that teachers and the people who work with teachers need to come to, that this realm of exploration really underlies a lot of the work that's already being addressed in the elementary grades, but tends to be implicit, invisible, and the work is really to raise it to the level of awareness.
So Bill has a... Oh, okay.
I think the question, too, that you were asking her, why did... I'm sorry, I think it came from both of you, though. Why was the last teacher, did we view that last teacher as having more mathematical knowledge? And I think, and when Diane and I were talking, and Lou, that in all of them you could see that the questions that were being asked is so very key. I think the fourth teacher that we watched did a little bit better job with the kinds of questions that once a student responded, then what's the next question to go to? And as we were discussing, that is something that is really missing from the texts or the curriculum. There are a couple that have some questions there, but if teachers want to change the way that they're teaching, they've got to know what kinds of questions to ask and then where to go with the responses that are given, particularly if they're incorrect responses that makes us squirrely and uncomfortable. You know, where are we going to go with that? And I really think that, and I don't know if it was, but it seems to me like most of those teachers were dealing with questions in a way that we don't see most elementary teachers dealing with, because it slows things down. And at that very last clip, at the end, you were like, whew, he finally got it out, you know. So is that something that is a key to what you guys are doing?
Absolutely, absolutely. I mean, so one of the things, and so there is, in terms of that fourth teacher and her mathematical knowledge, she does not have a degree in mathematics. She does not, I mean, but she has been working with us for a while in understanding deeply the mathematics content that she's responsible for teaching. Actually, when she started working with us some years ago, she was a kindergarten teacher, and she decided that she wanted to move into a higher grade because she wanted to be able to engage with the mathematics content.
Well, the conversation, she was making it conversation.
Yeah.
Go ahead.
No, you can.
Well, I mean, also, underlying and asking the right question at the right time is knowing what you're aiming for, knowing what your mathematical agenda is. And I think that's fairly clear to most of these teachers in these instructional sequences that they're undertaking right now. So it may not always be clear to them at every moment, as it isn't for any of us, but overall they kind of know what they're heading for.
Yeah, and so that makes it so that it's both knowing how to respond to what the students say, being able to connect to the student ideas, being able to listen clearly enough and be thinking about how what the student is saying can help move her agenda for the learning of the class forward. But there was also something about being clear about how the initial task is set up. And so it's not, but So it's not just responding to the student in the moment, but there is something about being attuned enough to the students over time so that they know how to frame the task initially to make it so that their students will be hooked in.
Well, I see that we're running out of time, and I wonder, can we get in a couple more quick comments?
Should we take another 5 minutes or so? Yes. Yeah, okay, let's do that. Or maybe even, let's go ahead and do that.
Sure. I just had a comment on clip 4. So you asked, what's a piece of mathematical knowledge that teachers need to have? That one's very interesting because there's a way of working with, what are these, Unifix cubes, anyway, whatever you call them. There's a way of working with these cubes where you would just allow kids to stick things together, any old how, to perform their operations, in which you wouldn't have a point to make in clip 4, because you would have already encoded in the way they're working with Unifix cubes the commutative and associative laws. So it seems to me, if you want to demonstrate the commutative and associative laws with these cubes, you need to establish a way of working with the cubes where it's important in the order in which you put the pieces together. Because the point of that last one is you could stick the green and the yellow together and then put the 1 on, or you could put the 1 on the green, was it? And then put that onto the yellow. I mean, the way to demonstrate the associative law with those cubes is to put them together in different ways. But so understanding that you need to model the order of operations with the way the work happens is going to be an important piece of knowledge for a teacher as they're watching kids. I imagine to some kids this would just seem obvious, what does that approve?
Right.
And somehow establishing a way of working where they see that there is something to prove, which that last kid didn't quite have actually, although he was, we were all cheering for him, but there was still somehow that point at which you were saying, what exactly is that to prove here when he was stating it?
I think that we do have on video that first class doing some of this to illustrate what's going on with the commutative property. But at a certain point also, and there is, I think, an issue to be explored more carefully here with regard to the standards, that if you're going to ask the kids to explain all of this with reference to the commutative and associative properties, then
that's what I'm saying.
That's
I'm
not
saying
what
the
you're
teacher
saying.
needs to understand that there's a way of working with these that would make it clear that there is something to prove.
Right.
Yeah.
Right. Okay.
Right. I think this whole area of when do students think there isn't anything to prove because it's so obvious? When do they think it's proven because they've looked at lots of examples? And when do they get to this point of sort of Vera's point of, but you can't disprove it with lots of examples because we can't do all the examples, so now we're stuck, so now what? And how does that transition get made? It is one of the things we're sort of interested in our new project, from being happy with the examples to not being happy with the examples to figuring out that there is, in fact, a way you can prove things in mathematics without trying all the examples. So, hi.
So, a couple of points. One is, I think one of the important things the teachers did was to give very clear formulations of the task, and it was very striking in the last example where she asked them to convince somebody outside the class who had not been privileged to witness all the work that they had done on many examples. So that framing of the task to persuade someone on the outside that this might be done, that formulation, or you might say, how would you persuade your younger sister or something like that? That's a very important kind of, it sort of says what the resource base for the reasoning is. You're not allowed to invoke things that are kind of shared and tacit knowledge among the class. So in each of the examples, I thought the task formulation was very carefully crafted. And in fact, in that last example, they don't have the tools yet to deal with infinite quantification. Why does this work for all numbers? And you're sort of begging them to use algebraic notation, which they don't have, of course. But I think it makes you appreciate that one of the important features of algebraic notation is that it incorporates infinite quantification. The x is not just a symbol, it actually gives you a way of talking in finite terms about an infinitely variable quantity. And then finally, I would, well, one comment about the it occurred to me there's a very nice task for middle school students here, which is you had one where you have a subtraction problem, and no, it was addition, where you take something away from one add end and add it on to the other add end. And then you could ask, what is the multiplicative version of that? Because the 10 times 10 by 3 and the 5 by 6 is exactly the multiplicative version of that. But that's a question, just making that connection would be a nice test at middle school level. But finally, I just want to draw attention to the amazing teacher who was listening so carefully to what her students were saying. Didn't say a word, waited and gave them plenty of space to bring out their ideas. She wrote them out on the board. And if you listen very carefully, all of them actually had pretty sound, at least the way I heard them, pretty sound mathematical ideas. But you rarely see a teacher wait long enough to let those things get on the table. And then finally, she made use of, although the task shifted, they were first talking about subtraction, she finally, but the task that they worked on was one brought up by that child. So it was a very impressive demonstration of listening to kids and making use of kids' ideas in the instruction.
I'm glad you said that. I just want to say one thing about that, because it relates back to the comment over here about questioning, but it's also about making decisions about when to question and when not, when to get clarification and when not. So you could look at the third grade example where they're trying to formulate their rule. There's a lot of places there, like the very first boy who says something about if you have a short answer. So you could stop there, right, and say, well, what do you mean by short? And that might be a perfectly appropriate thing to do, but she's having to make all these judgments as this class goes on about where are the places to stop and really probe what's going to benefit all of the students. So.
Hi, I wanted to say two things. One was you described.
You just turn it on, slide the switch up.
Oh, sorry. Just one comment and one question. You talked about students moving from specific examples to questioning, is that going to work for any number always? And moving from empiricism, and it was funny to me because in undergraduate mathematics education, research on learning in that area, that's still a question for us. Like, how do we get our undergraduates, our novice proof writers, to stop reasoning empirically? So it was, anyways, it's just one of these places that's actually a theme for us, K-16. You were asking us this question throughout your video clips of what is the teacher's work and then what mathematical knowledge is required. And we are, can I include you? We had a little trouble pulling those two things apart because we were wondering how you were thinking about work in that context. And just to give you an example, in your clip, so she has, the child says, what did he say, whatchamacallit, or whatever it is?
Whatever, doesn't matter.
Oh, who cares? Who cares and who cares plus one?
Yeah, okay. Yeah. So some of us use this term for a child who's doing an argument like that he's giving you a generic proof. Those are generic numbers, that those concrete things are placeholders for something that he can vary. And I kept thinking that the teacher would have to recognize kids who were holding concrete, had specific numbers but were reasoning generically, versus ones who were trying to, had concrete numbers and were not reasoning generically. Some who were having non-generic things in their work, but we're actually engaging in generic reasoning. You know, so there's these combinations, and it actually, and then what do you have to do to differentiate between that generic and non-generic thinking? And it just seems like it gets complicated if we try to pull it apart in terms of work and mathematical knowledge there. So I was wondering if you could say something about that. Sorry, it was a long question.
Well, one thing is that, yes, that is part of the work, is to be able to have a sense of where the child is at that time. Is this child actually making an argument for an infinite class, or is this child really still talking about particular numbers? But another thing just to keep in mind, which isn't just about, it's sort of a little bit tangential about the work of the teachers, is that those students who aren't yet wrapping their minds around generic proof or the challenge, the problem of proving something for an infinite class, are likely still to be getting a lot from the conversation in the class. That the students aren't all in the same place, and they can be still learning from where they are from the same conversation. So that some students might still be needing to, so this addition generalization in third grade might not be as good an example as the multiplication. But in the where the third graders are working on multiplication, and some of the students are making an argument for an infinite class, and other students are still thinking about specific numbers, those students who are still thinking about specific numbers are still doing important work from where they are in that same lesson. Actually, we'd like to make one other, say, just because it's fun. That we were thinking before about ending our talk with something fun. So this is just a little anecdote from the beginning of the first unit on multiplication and division in a class. The teacher was leading a discussion about multiplication as groups of things, and then one student asked, "Is multiplication related to division in the same way that addition is related to subtraction?" And then the first thing, so the teacher wrote to us about this because she was so excited about the ideas that were coming up in the class. So then she wrote that the first thing the next morning, another student walked in the door, marched right up to the teacher and asked, "You know that thing you can do with addition when you keep one number whole and add the other one in parts? Well, I was wondering, can you do the same thing in multiplication?" And so it's that kind of curiosity about the behavior of the operations that we're trying to cultivate in elementary school classrooms, and we're trying to work with teachers to learn how to leverage questions like these for the learning of all their students. So.